Hello, I'm finally back. Right, this is part 2 of doing the annoying integral, which is the integral from 0 to infinity of inverse tangent x divided by x cubed plus 1 dx. And last time we defined this integral function in terms of a. We kind of used Feynman's trick on it, differentiate it, and we got this. And then we used partial fraction decomposition on the integrand to get this, and then we solved for the constants. The variables, the coefficients, I don't know, whatever. The things that we need for the partial fraction decomposition. But the most important thing is that I'm back and I can actually do it because I've been so busy, but it's fine. Anyways, in this part, we are going to find an explicit representation of I prime of A. And let's just get started. And the way I'm going to do that is by just putting this in and then putting these into here. So let's do that. So I've just substituted in the partial fraction decomposition for the integrand. And you might notice that I've written things slightly differently. I've written the bounds out here. And the reason for that is if we had the bounds here and we just expanded it blindly, because the integral is a linear operator, so it's linear. When you expand it linearly, you're going to get something like this. So if you just don't have this and expand it like this might not converge on its own, and so might this, right? It might diverge, and they might only converge when they're in like one massive integral sign, and that's why we have to be careful. We can't just expand it while the bounds are there. This is why we're evaluating the bounds at last, and we are going to expand the integral as if it was indefinite. And I guess another problem is you kind of have to consider the fact that there are, constants of integration, but the constants kind of just absorb together after each of these, and then, they cancel out when you do the bounds. That's what you do normally on, definite integrals anyways. You ignore the constant of integration, and it works in this case. So we're just going to roll with it. And these integrals, I have named this one J1, this one J2, and this one J3, just so that we can easily keep track of them more. And yeah, so all in all, we have I prime of A is equal to J1. Technically, these are now functions of x because, the bounds, they don't have bounds right now. But I'm just not going to write, J1x. Who does that, literally? So J1, J2, and J3, just remember they are functions of x. And these bounds, they go from 0 to infinity for x as well. So maybe I should really write x to 0 and x to infinity, but that's fine. Yeah, so this is what we're going to do, and let's start with J1. Yeah, let's do it. So we shall begin with J1, and J1 is not bad at all. Let's just do it. So first thing we're going to do is substitute A and B into the integral / integrand. But we are also going to notice that A and B have a common factor of a squared over a6 plus 1. Because they have a common factor, right? So we can pull this out of the integral because that doesn't depend on x, does it? So I'm going to pull it out, and what's left in A is a to the 4th. What's left in B is -1. And the denominator stays the same. And we have a lovely integral with a quadratic denominator and a linear numerator. And that means we split the integral apart. So we can split the integral up into its two parts, a to the fourth x divided by the denominator minus 1 over a squared x squared plus 1 dx. And let's just do this at the same time, why not? So the left integral, it's a pretty clear u substitution. Let's just substitute u as the entire thing, because why not? And then du will be, well, 2a squared x. That should be it, dx. And yes, that should be it. And we see that we have an a to the fourth up top. That means when we substitute in, we're going to have an a squared left. But we also have a factor of 2. That means we have to divide by 2, because we have to multiply by 2 to get the 2, and then divide by 2 to balance it out. So our left integral is going to be, well, we have this factor here, is going to be a half times the remaining a squared times integral 2a squared x dx divided by u. And this right here is exactly du, and this whole integral is natural log u. So it's natural log a squared x squared plus 1. And technically, I should put, absolute value bars, but I know everything's going to be, greater than 0, so it's going to be fine, right? We're going to set a to 1 anyways, so that's fine. X is from 0 to infinity, that's fine, plus 1. It's obviously positive, so that's fine. And now we have the second integral, and what we're going to do is we're going to make use of this kind of identity here. So this integral, 1 over x squared plus a squared dx, is equal to 1 over a times inverse tangent x over a plus c. But no one cares about it right now. But, plus c is always so lonely. Why am I talking about that? Okay, anyways. Yeah, so we're going to try to put it into this form, but maybe I shouldn't have used a. I should have used something else, just because, we are using a in our thing. Let's use mu. I don't know, because mu is funny. Okay, and then, let's see. This integral, we can factor out a 1 over a squared. I'm sorry. We can factor out a 1 over a squared. That leaves us with x squared, and I hope you can see that's 1 over a squared at the bottom, which seems a bit complicated, but this is actually fine because this is now in the form of what we want, and we just have mu is 1 over a. So all in all, this whole thing here is going to be minus 1 over a squared times 1 over mu, which is a, so that's going to be 1 over a, times inverse tangent x over mu, which is xa, or ax, because, well, mu is 1 over a, so x times 1 over mu is x times a, which is ax. I don't know why I'm rambling on about this, but, that's J1, and that is J1. Yay. I have nothing more to say other than let's go do J2, because I don't know what I'm talking about anymore. But yeah, let's do J2. Right, so this is J2, and I can tell you that it's much worse than J1. But we persevere, and we get through it. So let's just do it. Right, we're literally going to do the same thing. So notice that C and D have a common factor of this, right? And again, we can pull that out of the integral. So that's fine. And what's left in C? Well, we're going to have 1 minus 2a squared left in C. X plus a squared plus 1, because that's what's left in D, divided by the denominator. And, I mean, it's the same thing. We have a quadratic bottom, we have a linear top. So, yeah, we can, do the same thing. It's just worse for some reason, because we've got, like, A's and stuff. The numbers aren't nice, but you know what? It's fine. So, remember how for J1, we got the quote-unquote left integral, and we did a u-sub on that. Well, if we did the same thing, it wouldn't work as well, because we have an x squared minus x plus 1. And differentiating that gets us 2x minus 1. And we don't have a 2x minus 1 in the numerator, so what do? Well, we make one. And we are going to use our only x right here. And first of all, let's try to get the 2x part. So, to get the 2x part, we are going to multiply and divide everything by 2. So, we are literally going to do 1 over 3 times a to the 4th minus a squared plus 1. That is our factor right there. And then we are going to divide this by 2 and multiply the top by 2. Right, so that's going to be 1 minus 2a squared times 2x plus a squared, not plus a squared, plus 2a squared, because we're multiplying everything by 2, plus 2 divided by x squared minus x plus 1 dx, because the denominator stays the same. And we have the 2x. Now we need the minus 1 part. How do we get the minus 1 part? Well, currently we have 2x of these. If we subtract one of these, then we get 2x minus 1 of these. So if we subtract one of these, we have to add back one of these, to balance things out. So we are going to have our factors at the front, and we are going to subtract one lot of 1 minus 2a squared. That means we have to add back 1 minus 2a squared. And, oh my word, the 2a squareds cancel out. Would you look at that? And then that becomes a 3 at the end. Because why would it not be a 3? It just wants to be a 3. Just let it be a 3. And now we can do the same trick as we used for J1, which is split it up into 2 integrals. Maybe I should write, maybe I should absorb this, silly thing, that half there, and we'll deal with it in a bit. So we have that, and then we are going to split it up into 2 integrals, which isn't bad at all. Bracket x squared minus x plus 1, and plus, let's put the 3 out, 3 times integral 1 over x squared minus x plus 1 dx. And again, let's just do them at the same time. So this, we're going to do a u sub, u equals x squared minus x plus 1. That means du is 2x minus 1 dx. Aha. And now we can solve for the integral. So our factor times the integral. Well, we have this thing here, which we'll pull out of the integral for now. And we have u at the bottom and du at the top, so that's going to be ln u. And of course, u is x squared minus x plus 1. And yeah, that seems right. And now we do this bit, and same thing, we try to get it into the form we had, but now it's going to be a bit different because, well, first, to get it into somewhat that form we had, we have to complete the square, and that will be equal to the integral of 1 over, to complete the square, we divide the middle coefficient by 2, so that's going to be x minus a half squared, and how much do we need to get to 1? Well, a half squared is a quarter, so we have 3/4 left, right, to get to 1. And that is our completed to the square form. And what you can kind of do is substitute this as u, but all you really have to do at the end because, well, in this case, u is x minus a half, but du is just dx. It doesn't really change much. So all we have to do is write this in its, inverse tangent form, which is equal to, because root 3 over 4 is, well, root 3 over 2 squared, right? This is going to be 2 over root 3. Remember 1 over mu, because this is our mu right now. So 1 over mu times inverse tangent x minus a half over mu, which is that, which is a bit weird. So we are going to flip this upside down. So that will be over root 3 times 2, right? And then we're going to distribute the 2 in. So that's going to be 2x minus 1. 2x minus 1. Ooh, that's a lot of algebra. I hope you follow. If you didn't, just replay it. Because, yeah, you know what? It's fine. And then we multiply by 3. So it's going to be, it's going to be 6 over root 3. But, 3 over root 3 is just root 3. Because 3 over root 3 is root 3. Right? And then that means this is just 2 root 3. Times inverse tangent 2x minus 1 over root 3. And that's our J2, I think. That is our J2. So, I don't know, I'm sorry if it was like anticlimactic, but, anyways. J3 now. Yes. Well, J3 is surprisingly easy, because E doesn't depend on x, so we can just pull it out. And that leaves us with this integral, 1 over x plus 1 dx. And I think we all know that that's ln x plus 1. So, that was very anticlimactic, but yeah. You know what? Let's put them all together. So we have I prime of A being equal to J1 plus J2 plus J3. And we have to take the bounds. So it's going to be literally just everything I write down afterwards, and then take the bounds. So that's going to be a squared over a to the 6 plus 1 times 1/2 a squared ln a squared x squared plus 1 minus 1 over a inverse tangent ax. If you're wondering, I'm not remembering this. I'm like literally just copying off my notes, but it's fine. So that was the J1 bit. This is now the J2 bit, which is 1 over 6 times a to the 4th minus a squared plus 1 times 1 minus 2a squared, natural log x squared minus x plus 1 plus 2 root 3 inverse tangent 2x minus 1 over root 3. And the J3 bit, which is quite simple. This is just E times ln x plus 1. So negative 1 over 3 times a squared plus 1 times ln x plus 1. And this entire thing, we will have to take bounds, which we will do. But I'm going to record that part 2 days later, which is hopefully when the video comes out. So, time skip. See you then. Hello, so this is now 2 days later, and remember that we have to evaluate the bounds. And this is from x goes to 0 to x goes to infinity. And this bit was our indefinite integral, and now it's to take bounds. So we're going to evaluate the limit as x goes to infinity, subtract the limit as x goes to 0. And what I'm going to do is evaluate this part first, because it's a bit easier. So let's do that. Right, so the limit as x goes to 0, let's limit this whole thing right there. Now, why do I think that this is easier? Because, well, take a look at these ln parts. Well, I call them ln parts because we'll use them. I call them ln parts for like the infinity thing. Anyways, if you take a look at these ln parts, they all die when you set x goes to 0. And why? Because look at this, for example, a squared x squared, that becomes 0 if x goes to 0. And then this whole thing becomes 1, and ln 1 is 0, of course. So this whole thing just dies, right? And then same thing here, x equals 0, this whole thing becomes 1, this just goes, x equals 0, this whole thing becomes 1, and then this goes as well. And now let's take a look at this part, right? If you set x equals 0, then ax is 0, but inverse tangent of 0 is also 0. So this goes as well. And then this entire term is just non-existent now. And, well, the same with this, actually, because the ln bit's already 0. That means we're really just left with, let's see, the limit as x goes to 0 of, should we do I prime of a? Nah, because, well, I prime of a is not, it isn't this, but it's the thing after we take bounds. So let's just write limit as x goes to 0. A bit of abusive notation, but like it's fine. Yeah, so that will really be equal to 1 over 6 times a to the 4th minus a squared plus 1 times 2 root 3 inverse tangent 2 times 0 is 0 minus 1 over root 3. And then because inverse tangent is an odd function, so this negative can be pulled out front, and inverse tangent of 1 over root 3 is pi over 6. So in the end, we get negative 1 over 6 times a to the 4th minus a squared plus 1 times 2 root 3 pi over 6. And maybe we can, like, clean this up a bit. Let's see. What can we do? Can't really do anything. I'm just going to leave it like that. So, yeah. I mean, you might get annoyed if I don't, turn that into a pi over 3, but whatever. Right, so that is the limit to 0, and now we will find the limit to infinity. So when we take our limit to infinity, we are actually going to split this up into 2 parts. And as I said, I used the terms ln part and arctan part for the 2 parts, and that's what we're going to do. So if we only consider the terms, like if we multiply these in, and then we only consider the terms with the ln, and call that, well, let's just say what we're looking for is the limit as x goes to infinity of the ln part plus the inverse tangent part. So we've got terms with ln in it, they're all packaged in there, and then the terms with inverse tangent, they're all packaged in there. And if ln and arctan, if the both parts converge, that will be equal to the limit as x goes to infinity of the ln parts plus the limit as x goes to infinity of the arctangent part. And it turns out they do converge, so we will calculate this instead. And yeah, so we'll start with the ln part, and yeah, let's do it. So for the ln part, we can just, well, we ignore the inverse tangent parts, so let's just get rid of those. And, oh, annoying. And I'll copy it down so we have something, easier to work with. So let's first take a look at the ln part, right? I've written everything horizontally, and everything should be better to work with. So let's start. We are going to manipulate this expression such that the entire thing converges. I mean, the entire thing already converges, but, we need to see that and evaluate it. And how are we going to do this? We are going to leverage this property right here. Right. If we have ln A minus ln B, that's ln A over B. And if this thing converges, then this thing converges, right? So we'll make use of that. And that means we kind of want to, like, merge everything together. Like, we want to put the ln's, you know, next to each other like that. And to do that, we have to get rid of these stupid denominators, or rather make them, you know, compatible. And the way we're going to do this is we're going to use this kind of identity. I think I used it in part 1 as well, just, you know, for the partial fraction thing, yeah. But, yeah, we're going to make use of that, and this is really convenient right here, these two, because we can just multiply the top and bottom by, you know, the respective other one, and we'll get a to the 6 plus 1, just like the one in front. So, for this middle one, let's multiply the top and bottom by a squared plus 1, and we'll get our needed denominator at the bottom, a to the 6 plus 1, and same thing here, multiply top and bottom by the a to the 4th thing, and there we go. Right, so we have our needed denominators, but how exactly are we going to combine these together if, you know, the numerators are still different? Well, our trick lies here. Let's see if we can evaluate this to something better. So, let me just copy down another row. There we go. It has been copied. Now, before I mess with this middle bit, and as you can see, I've moved this up to the top, which will help us in a bit. I just want to combine these two a squareds, just because it will help us again. But yes, now our trick lies within this, and let's expand it to see what we get. So a squared times 1 is a squared times negative 2a squared is negative 2a to the 4th, 1 times negative 2a squared is negative 2a squared, and 1 times 1 is 1. And then we can combine, you know, the a squared and the minus 2a squared. That will become minus a squared. And how exactly am I going to use this? Let me just put that down. Perfect. Right. How am I going to combine this with this, or this with this? Well, you might spot it. I don't know if you can spot it, but here it is, right? So, we have a minus a squared plus 1 and a minus a squared plus 1. Kind of missing an a to the 4th, right? What if I squeeze out an a to the 4th using this? And if I split this up into a to the 4th, right, and minus 3a to the 4th, that gives us the same thing, right? That means I can get this part to combine with this part and use this a to the 4th remaining to combine it with this part. How convenient. My thing is being so messy right now, but I'll just get rid of some of these lines. That means we split this whole thing up into negative 3a to the 4th plus a to the 4th. And let's write another row down, but I will separate these two. There we are. I've written another row down, and I've split this fraction up into 2. Now, let's start combining things. So, we have this bit that is suitable to combine. You might not see why it's suitable to combine just yet, but let's manipulate this a bit. So, if I multiply this a half into the denominator right here, and for this fraction here, I'll simplify the 3 and the 6, and that 3 will go. that will become a 2. Maybe I should have done that in black. There we go. 2, and that negative sign, that can be put out front. And as you can see, we have a perfect match, and that means we can factorize it out. Twice a to the 6 plus 1. And then we have a natural log a squared x squared plus 1 minus natural log x squared minus x plus 1. And we will leverage the property of logs. We can combine this into a fraction, so that will become natural log of a squared x squared plus 1 divided by x squared minus x plus 1. And we'll just leave that for now, right? We've still got the right side to take care of. So, the right side. We've got a good numerator here. It's our denominator slightly different, and what I'm going to do about it, how am I going to deal with this? I am going to turn this into a 6, but I can't just magically turn that into a 6, can I? So turning that into a 6 means that I've divided by 2, and that means I have to multiply by 2 as well. So I'm multiplying by 2, and by the property of logs, I can throw this 2 into the power of x plus 1. So that means that will become x plus 1 squared on the inside, right? And then now, again, we've got the same factor at the front, and we can factor it out. So we've got a to the 4th minus a squared plus 1 divided by 6 times a to the 6 plus 1 times natural log x squared minus x plus 1 minus natural log of x plus 1 squared. And x plus 1 squared is x squared plus 2x plus 1. And again, we leverage the property of logs to combine this into one giant fraction. Well, not one giant fraction, but one giant log into x squared minus x plus 1 divided by x squared plus 2x plus 1. And now we are ready to take the limit to infinity, because this fraction, we can compare the degrees of the polynomials, because this does not depend on x's at all. So I don't care about this factor at the front. It's only this bit inside the log. And of course, if they've got the same degree, as they go to infinity, it converges to 1. A natural log of 1 is 0, so that just goes away. And similar thing here, but we actually have something. So the degrees are still the same, but oh yeah, I forgot to mention that the coefficients, they're 1 at the front, so that's why it converges to 1. But in this case, it's not 1. We have an a squared at the top and a 1 at the bottom. That means it converges to a squared because it's the same degree. So it converges to a squared, and that means it converges to a to the 4th, 2 times a to the 6 plus 1 times the natural log of a squared. And of course that squared can be thrown back out to the front, becoming a 2 here, and that cancels out with a 2, and that leaves us with a to the 4th divided by a to the 6 plus 1 natural log of a. And that is what the ln part converges to, or limits to, I guess. Wow, that was a bit of algebra there, but we still got the arctan part to do. That should be easier. So I'll see you after I clean this up. So this is the arctan part. Should be relatively easy, because, well, let's just see. So inverse tangent ax. When x goes to infinity, ax goes to infinity, and the limit as arctan goes to infinity, it's pi over 2. So this bit is just pi over 2. Similarly, inside bit goes to infinity, inverse tangent goes to pi over 2. And all in all, we basically just get, so negative, that negative pulled in front, a squared divided by a, that's just a, divided by 2a6 plus 1 times pi. And plus 1/6 times a to the 4th minus a squared plus 1. And then root 3 pi, because these 2's cancel out. And that is literally it for the arctan part. So we are ready to evaluate I prime of A. How exciting, let's do it. So, I prime of A, let's go. I prime of A is equal to, is equal to the limit as x goes to infinity minus the limit as x goes to 0. And of course, we had the ln part plus the arctan part. And then we subtract limit x goes to 0. And the ln part, we got a to the 4th divided by a to the 6th plus 1 times ln a. The arctan part, we got negative a over 2 times a to the 6th plus 1 times pi. But, I mean, that's just pi over 2, so I'm just going to write that there. And then plus 1 over 6 times a to the 4th minus a squared plus 1 times root 3 pi. And the limit as x goes to 0, we got minus negative 1 over 6 times a to the 4th minus a squared plus 1 times root 3 times pi over 3. And of course, we can, we'll just copy this down, but we can rearrange like the last 2 bits into, the minus and minus, they become plus, and we can factor out a 1/6 of a to the 4th minus a squared plus 1, and we have a root 3 pi plus root 3 pi over 3, and maybe I can factor out a root 3 there up to the top, which leaves us with pi plus pi over 3, which is 4 pi over 3. There we go. And, maybe we can simplify a bit. 2 and 3. So, that becomes 2 root 3 divided by 9 times pi. And yeah, that's I prime of A. We've found an expression. The thing is, we kind of have to find I of 1. That means we have to integrate that with respect to A, but that's for a later video. Thanks for watching. I'll see you next time. Hopefully it won't be like another 2-week wait. I'll try to catch up. See ya.